Alrighty, we're going to finish up chapter 2 here. And 2-4 is one of those where we've scheduled 3 days, but we probably could have gotten away with 2 days if we didn't have to give your test back. And so, probably tomorrow I might try to get your test back to you. So we'll zip through a little bit of this stuff today that is a lot of review. It really is. But there's certain parts we're not going to zip through, and that's going to be polynomial long division, because I'm sure some of you are thinking, oh my gosh, that was one of those things that I remember not liking. It's not that it's difficult, it's just there's a lot of little steps where you could make a mistake, So we're going to use long division and the division algorithm today. We're going to talk, hopefully we'll get to the remainder and factor theorems, and use the rational zeros theorem. That might be in tomorrow or the next day, and definitely the upper and lower bounds. We'll be talking about that stuff tomorrow. So long division really can, bless you, be connected back to long division that you did in grade school, where you look at this and you say, okay, I'm not really trying to figure out how many 32s can go into 3,587. Instead, I think, well, this is going out to the tens position, so I'm just going to use these first 2 and figure out how many 32s can go into those first 2. And there's one of them. And then we always subtract it. So we said, well, 35 minus 32, that's going to give me 3. But we weren't done, obviously, because we hadn't dealt with the entire number yet. So the next thing we did was said, well, let's bring down another digit so that we can think about whether or not 32 will go into that number. And 32 will again go into 38 once, and we subtract again. And once again, we realize, well, we're not done because there's still a 7 up there that we haven't used yet. So that'll give us 67. And we say, well, now look at that. We can actually take 2 of those and put them in there because that'll give us 64. Which gives us, my remainder is a little bit off here from my arrow, but that would give us a remainder of 3. So our quotient, our divisor, our dividend, our remainder, all of those are important pieces of vocabulary when we start talking about the more complicated process of polynomial long division. So the divisor is, what are you trying to divide into this number? And then your dividend is the number that you had to start with that you're trying to figure out. How many of these will go into this? And your quotient is the answer that wouldn't be a fractional portion. That's what our quotient is. And then our remainder of 3, we actually learned that what we need to do is think, okay, that's our remainder, but that's a portion of what we were trying to do, exactly, which we divide that by the 32. So it would be 112 and 3/32 that we're looking at there. So the process is very, very similar when we talk about polynomial long division, but obviously it takes on a little bit different form. So if we start talking about, okay, now we've got a polynomial and we want to divide it, we do still use the good old division symbol and all of that. Like so. And we do just focus on the digits that we're working with at any given time. That means if I have 3x plus 2, my focus is just going to be on, actually, the first one of these, but in the chunk of the first 2 terms that I see here. And what I have to do is think of my 3x plus 2 and focus on getting rid of the first term every time. That's your focus. How do I get rid of my first term? So I need a 3x to the 3rd. That way I can kind of move this down just like we did with the division up here. We worked with the first couple of digits, got it taken care of. Oops, now we're in the second digit position. We took that first digit out of play. And that's what we have to do with polynomial long division. So I look at this and I think, I have a 3x, but that's going to need a couple more x's to make that work. So I'm going to have to multiply that by x squared. But we have to multiply the whole thing by x squared, not just the first term. So that will give us 3x to the 3rd plus 2x squared. Now, it did the job. I have a 3x to the 3rd there. So we write what's been working up above because that's part of our answer. And we usually line them up so any cubics are here, squareds are here, x's are here, and then constants are going to be in the back. And then we realize, wait a minute, when we did division, we had to subtract. Yeah, and that's going to be easy to make a mistake on. You know what the subtraction usually is. So what I'll usually tell everybody to do is just change these to negatives and think addition. Change the signs and add those together. That way you won't accidentally add something that you're supposed to subtract. So now our 3x cubed minus 3x cubed is gone. That's exactly what we wanted to happen. And we have 5x squared minus 2x squared, which would be 3x squared, or you could think of it as 5x squared plus a negative 2x squared. But there it is. And we do the same thing that we did with long division before. We say, well, we're not done. I haven't even touched the 8x and the 7 yet, so I better bring that 8x down here and give it another try. Well, I'm still going to start with 3x plus 2. Still my divisor. But now my focus is, how do I get 3x to be 3x squared? How do I get it? Need an x. Multiply everything by x, so 3x squared plus 2x. It did what it was supposed to do, so I'm going to put that little blue x up on top. And then I have to change this so that I'm subtracting, which would be adding a negative. And changing those signs makes it easier to remember. So 3x squared minus 3x squared, gone. 8x minus 2x is 6x. What should we do next? Pull the 7 down, exactly. We're finally at that last digit. So now we have our 3x plus 2. What's going to be required to make that work? And that will give us 6x plus 4. It did its job. It's going to get rid of that first term for us. But we have to change the signs and add. So what's up with the 3? Things were going really well, and now all of a sudden we got a 3 down there. What is that? It is our remainder. So it's going to be 3 over our divisor. So plus 3 over 3x plus 2. And our answer would be x squared plus x plus 2 plus 3 over 3x plus 2. That's called the fraction form of the answer, by the way, because we've got this little fraction piece hanging on in the back. Because they're going to ask us to write our answers in 2 forms. They're going to say write it in polynomial form and write it in fraction form. Fraction is already what you're used to. This is what you've done before. Polynomial form, just a little bit different. So, to check our results, math has to work forwards and backwards. It has to. So this says, if we know that the division worked, well then when we multiply this stuff back together, we better get back to the original. So here's what we had. We had a 3x plus 2. We said that the answer should be x squared plus x plus 2. But that it won't work perfectly. How did we know it would work perfectly? It had a remainder, so we're going to have to add that remainder back on in order to get this to work. And this is just multiplication. Granted, it's kind of putsy multiplication, but it's multiplication because we're going to distribute 3x times everything in the other set of parentheses. We're going to take the 2 and distribute it times everything in the parentheses. And we're not going to forget about that little 3, because remember, this isn't going to work without that remainder. And then we'll combine like terms. We have the 3x cubed, we have 3x squared and 2x squared for a grand total of 5. We have 6x and 2x for a grand total of 8. And then we have our little 4 and 3. Now that has to be our dividend or we messed up. And our dividend was 3x cubed plus 5x squared plus 8x plus 7. There it is. What we just found was the polynomial form of our answers. Which basically, polynomial form is kind of like, if you were going to check this, what would you have to do? You know? How would this work if you wanted to check your answer? And we'd have to take our division and change it into multiplication, but remember to tack on the remainder. So your homework, I know, asks for both forms. Each one of the problems says, give this in polynomial form and then give this in fraction form. So now that we know what they are, I mean, it's not that big a deal. So division algorithm for polynomials says, f of x and d of x are some polynomials with degree of f greater than or equal to the degree of d, which just means you can actually do the division. And it says d of x cannot be 0. Obviously, we can't divide by 0. So then there are unique polynomials q of x and r of x called the quotient and the remainder, such that if we multiplied that d of x and q of x together, just like we did in the last one, and then added our remainder, we would get back to the original, which would be f of x. And like it says, we're either r of x equals 0 or the degree of r is less than the degree of b. It's just going to happen naturally that when we divide, our degree ends up being less, our answer degree. So f of x in the division algorithm is our dividend. D of x is the divisor. So dividend, what number are we trying to divide? What polynomial are we trying to divide? And then the divisor, d of x, what are we going to divide it by? So the summary statement in the division algorithm will sometimes be written in the fraction form instead. And that was actually the way you first learned how to do division, was by writing, hey, here's my quotient answer, and then I'm going to put that remainder over my divisor. So that's going to be our fraction form. And here it is again, exactly what we did before. When we did our division, exact same problem, and we said, hey, here's the quotient, that's what we would get, but we've got this little remainder and we have to put that over the 3x plus 2. So there's our fraction form. So example 1 says, let's use polynomial long division. Use long division to find the quotient and the remainder for 2x to the fourth minus x to the third minus 2, if that is divided by 2x squared plus x plus 1. And write a summary statement in both, put them both on there. So we want to take 2x to the fourth minus x cubed. And as you're writing it down, you should notice there's stuff missing. You know, if this is in standard form, I'm missing my x squareds and I'm missing my x's. Now sometimes it doesn't matter and you could just put the minus 2 on there and you go on your merry way. But most of the time it's helpful to put in some placeholders for those positions so you don't accidentally mess up, you know, as you're going through it. Now this time we have a trinomial put into this thing. But it's no different than what we did before. Our focus is always on that first term, you know, making that first term disappear. So if I have 2x squared plus x plus 1, what's the first thing I'll need to multiply by to get rid of that first term? X squared. You can already see how it's kind of helpful to have that x squared placeholder in there. Now, important step, change the signs. Think about it as adding. 2x to the fourth plus a negative 2x to the fourth will be 0. It worked. Let's put it up here. And then we just go with the rest of it, see what we have left. So negative 2x to the third minus x squared. What would we normally do? Yeah. There it is. So we've got that. Now I'm going to change colors here. I'll stick with black for a second. So what should we multiply by next? Negative x. Have to match that first term. Did what we wanted to do. We match with that first term, so we're going to put our little minus x up there. Change the signs and think of it as addition. 2x to the third, gone. That piece is gone, but so is our x squared this time. So we just have an x. What would we normally do? Problem? This is what they were talking about with the powers. I mean, we've gotten to a point here where we can't do anything else with this because we can't multiply 2x squared by something nice anyway, that would make that x minus 2. So this is just going to be a really ugly little remainder over our trinomial. So fraction form is exactly what we have up there. Scroll up past things. That's our x squared minus x. And then our nasty little remainder plus x minus 2 over 2x squared plus x plus 1. Polynomial form is, if we were going to check this, what's the math we would have to do? Well, we'd have to take our 2x squared plus x plus 1, and what would we multiply that by? Yeah, because we'd have to add the remainder on it. Yeah. So again, fraction form is what you've already learned. Polynomial form is just, hey, if we were going to check this, what would we have to do? What math would we have to do to get that? So that's polynomial on division. And it takes a while. And like I said, it's not necessarily the toughest thing we've ever learned to do, but there's also a lot of little steps where you could make negative mistakes and that kind of stuff. So you kind of just have to go tortoise method, which is, slow and sure is slow and steady, going to win the race here. All right, an important case of the division algorithm occurs when the divisor is of the form d of x equals x minus k. Now this paragraph sometimes blows people away, but that means this, x minus k. Hey, we've dealt with that a lot. I mean, that's when we're factoring. We get x minus h, x minus k, all of that good stuff in there. And it says this is a special case. Well, of course it is, because this is how we find zeros. This is a really special, important case. And it says where k is a real number, because the degree of x, d of x equals x minus k, is degree 1, and the remainder is a real number. So what does that mean to us? Well, f of x equals, so we've got something linear here, and then we have a quotient plus r. If it's a 0, we put it in here, and this gives us 0. 0 times anything is 0. This is just going to come out to be r, the remainder. So evaluating when you know that it's that 0, if you put k minus k in here, that's the whole reason we found the 0, was so that that set of parentheses would be a 0. That's just going to give you the remainder. That's called the remainder theorem. So our understanding that, hey, if we put one of those factors in there, what we have left is just the remainder. That's all it is. So f of k equals r gives us that remainder piece. If a polynomial f of x is divisible by x minus k, what you're going to get is your remainder when you get done with it. That's exactly what we've been doing. We're trying to see if we put this factor in, what are we going to get? And what's our remainder? So we're actually getting both pieces. This enables us to find the remainder of a polynomial when it is divisible by x minus k. It just makes it a little easier. as we go through. So this says, find the remainder when f of x equals 3x squared plus 7x minus 20 is divided by x minus 2. Find that remainder. Well, what the remainder theorem just told us is, we can make this easier because all we need is the remainder by just saying k is 2 and plug 2 in and see what we get. That's what the remainder theorem says. It says, hey, if you know this is going to be your divisor, then go ahead and plug the 2 in, but it only works for linear. That's what's important here. This is x to the first. Works for linear. So if we put a 2 in for all of our x's, that will get us our remainder.
Good. So, is there anybody that else that's it?
See what our answer is. 2 squared is 4. 3 times 4 is 12. 12 plus 14 minus 20. So that would give us a nice little 26 minus 20, which means our remainder is 6. So if all we want is the remainder, we can do this shortcut. You know, if we don't care what the quotient is, we just want the remainder, we can do this little shortcut. So I don't think you need me for B and C. I think I shall hit stop on the record here and have you quickly. The 0, we have found a factor. Now that is important and helpful for lots of reasons. First off, we already know there are a lot of things out there we can't factor. And that's because, you know, we look at it and we say, wow, this has 5 terms. All I know is if you have 4, you can do grouping, but it has 5. This will allow us to use the graphing calculator to find one nice 0 and maybe get it down to where we can factor it. So it's important that we realize those zeros are a big deal. So important and helpful because when we get a remainder of 0, we have ourselves a factor. Ooh. And like it says, if we can find a remainder of 0, that factor divides evenly into our polynomial. And this indicates that k is a solution, an x-intercept. You know, all of the, well, we've called them roots before, all of those good things. An x-intercept of the growth of the polynomial. So like it says, occasionally we've used the table feature to go through this. You use the table feature of the calculator to find those remainders of several division problems. And what it's doing is it's showing us we can put 3x squared plus 7x minus 20 in there. And then we can look at the table to see, oh look, that one comes out to be a 0. And that will tell us that if we have x plus 4, we have a factor of 3x squared plus 7x minus 20. And that gives you a cheater's method for factoring. If this is -4, that means x plus 4 was a factor. Now, that means with a little bit of backwards thinking, you could find the other factor very easily by saying to yourself, self, -5. It has to give me this. If this is a 1x, that has to be a 3x, because that's the only way that's going to happen. And if this is a 4, that has to be a -5, because it has to give me -20 in the back. Gotcha. Cheater's method of factoring, right there. And now we can get the other 0 very quickly. Even though this one probably wouldn't show up on our normal table, we could say, hey, we'd set this equal to 0, we'd add 5, divide by 3, boom, there's the other 0. We've got it. So finding those factors, finding when the remainder is 0 is huge. You know, it is huge. So sometimes we will use the calculator just kind of to get us started and say, okay, here's a factor. Now, let me divide that one out and see what's left. You know, what do I have? Is the rest of this factorable, or am I going to have to go with the old GC to get the rest of it? So the factor theorem up here says a polynomial function f of x has a factor x minus k if and only if f of k equals 0. So if we put that k value in and our remainder is 0, then it is a factor. And it says using the ideas of the factor theorem, we can take a new look at example 2. We have a known factor of x plus 4, and like I said, that it's a little easier than this, but they're trying to say, if you know that x plus 4 goes into this, use it to divide it, and what will be left will be your other factor. I think that's a little slower than just using the cheater's method, working backwards, but we would multiply this by a 3 and an x, and that would give us 3x squared plus 12x. We know it's working. We change the signs. We start again and say, well, now I need a -5. It worked. We change the signs. And there's our other factor. Teacher's method is definitely faster. But it does give us another way to find the other factors that we have. So now we would also have a known factor of 3x minus 5. So this process is quite helpful for polynomials of degree 3 or higher. You know, it has a lot to do with how many terms we have, but it also has to do with the powers of those terms, whether or not something's going to be easy for us to factor. So we're looking for factors, and we're looking for zeros because graphically we are finding the x-intercepts. So for a polynomial function f and a real number k, the following statements, they're synonymous. We have a lot of different names to talk about those zeros because it's, what are you talking about? What's the topic? Are you talking about the graph? Because then you want to call them x-intercepts. Are you trying to find an answer to a word problem? Because then it's a solution. So x equals k is a solution, could also be called a root depending on the problem you're working on. It is a zero, it is an x-intercept of the graph, and that makes x minus k one of your factors. So I guess probably the part that if anybody misses anything on this, it's usually that those factors come in the format of x minus k. You have to always remember I'm going to use the opposite when I do my division. Well, when I use my remainder theorem and I put my number in to find the remainder. So x minus 2 is a factor, special case, x minus 2, x minus k. Do you remember another method to find both quotients and remainders without long division? One person said it, synthetic. It's math magic. Synthetic division is just math magic. It's one of those things we spend a couple of days on and people forget about it, but synthetic is so cool. It's a way to make long division seem like it's archaic. You know, there are so many different ways to do it. Here's the problem though. You cannot use synthetic division with everything. You can't do that. Your divisor, to use synthetic, your divisor has to be in the form x minus k. So if you want to try synthetic with 2x minus 1, can't do it. You know, it has to be in that form x minus k. So here's an x minus k example, and it shows exactly what we've been doing with long division. And then it says, well, what if you didn't worry about the Bayer variables? You know, wouldn't you still do the same math with the numbers to get what you needed? And you would. So then we say, well, hang on a second. Can't we just notice that I've got a -3 and I'm using these numbers, -6, -9, and -12 to get my answer of the 2, 3, and 4 up there? And you're going to notice this book writes synthetic a little bit different than your Algebra 2 book did. And right now it's really hard for me to remember how your Algebra 2 book did it. I think your Algebra 2 book did this.
Yep.
Yeah. So different books will do this different ways. I'm sure you've already noticed that I'm teaching you transformations a little different than you got from Mr. Michener and Mrs. Gosha. And that's because we're going to find out later on there are a lot of ways to do transformations and they can still be right. But you have to know why they're right. And that's why I have to see them the way that I do. So, synthetic, huge time saver. Also can usually be done just in your head. You know, you wouldn't ever have to grab a calculator to figure out what those pieces are. Unless we've got really nasty word problem numbers, then generally things are good. So this is math magic. It's this waving a wand. Bam, I get my answer. Love that math magic. All right, so now we're going to divide this one, and it says divide 2x cubed minus 3x squared minus 5x minus 12 by x minus 3. And then we're going to write a summary statement of what we have. We're going to say what the answer is. So this is the first thing I check to see, can I use synthetic with this problem? Absolutely. That's in that x minus k. So then I think, well, what would k be if this is x minus k? 3. So 3 for this book is going to go in this kind of little half box thing. Now, synthetic, great, fast, and easy. If you remember that you have to have a representative for each of the powers all the way down. If something's missing, you have to put a 0 as a placeholder. Even if it's the constant at the end, you have to have a 0 in that place. So as I'm looking at this, I'm thinking 3, 2, 1, 0. Good. I'm not going to miss anything this time. They're all there. And you just take the coefficients. And synthetic works this way. Inside the box, add. Outside the box, multiply by k. Inside the box, add. Outside the box, multiply by k. We start with that leading coefficient. It gets its name for a reason. It's the leading term. We are outside the box. We multiply by k. 3 times 2 is 6. Then we go inside the box. We're inside the box, and we add. We're back outside the box. We multiply by k. We're inside the box. We add. We're outside the box. We multiply by k. We're inside the box, and we add. So the question is now, I mean, that was nice and easy math. What do we have here? You know, what is this? This is our answer. This is our quotient. So we have to remember that whatever we get in this last position, that's always our remainder. This is excellent news. Our remainder is 0. And then we work up by degrees. So degree 0 will be a constant. Then we'll have an x to the first, and then we'll have an x squared. So this is 2x squared plus 3x plus 4. And it said write a summary statement in fraction form. So now we're like, well, that was our answer. Did we have a remainder? No. Well, that is in fraction form then, because we'd say plus 0 over blah, 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 and that doesn't make any sense. So this is our fraction form. Right here. This synthetic. Again, only works with factors of x minus k form. Can't use it if there's a number in front of that x. It doesn't work. So obviously, we would prefer to use this all the time if we could, but we can't because it must be in x minus k form. Never. That's why we still have to learn long division. We don't have a choice. We need something else. So in order to use synthetic, x minus k has to be. And in fact, for today's assignment, you have to do long division for all the problems that we give you. It's just one of those things, because we have to be able to do it. We've got to find all those factors. Whoa. So we've got extra examples, whatever kind of the block. Oh, we're good. 2 polynomials are given. Use either synthetic or long division to divide p of x by d of x and express your answer in 2 ways. Oh my gosh. That looks awful, doesn't it?
I think I'm gonna go home sick.
Yeah.
Right now.
Not
My
good.
parents got sick.
But what is this really saying? I want you to think about this with your partner. Take a second and figure out which form that is in the red and which form this is in the green. So talk about that with your partner. Those are our 2 forms. Which is which?
Which one is what?
Left one's polynomial, right one's fraction.
My sister has it so easy. She's learning long division.
Why are the letters in math?
But
And the so it's the 1, 2, 3.
awful.
And you see how important it is if you can get long division down.
Because there's terrible customers here. Daily. Terrible. Like, you just have to turn around and be like,
I remember tears for people doing long division. All right, everybody, red one is which type? Polynomial. Polynomial form. So the green one is the fraction form. Big shocker, there's a fraction here. R of x over d of x. So there it is. So let's look at A, and I want you to tell your partner whether or not we could use synthetic for this problem. No. Yes. And what are you going to use for the little box number? Do it, and then check your answer with your partner.
right now. All right.
Tell your partner why my answer would be wrong if I left that on.
It's not in fraction form. It's in blah, blah, blah.
Shut up. We have to use that synthetic division to get the coefficients that we need. And then we write our polynomial. All right, now I know you've been looking forward to this. Tell your partner whether or not we can use synthetic for B. So go ahead and do the long division and check in with your partner when you're done and see if you're both getting the same thing. Okay, now the directions did say that we should write our answer in two different ways. So we'd have to go back and say, okay, we did the fraction form of this one already. The polynomial form would be x minus 1 times x squared plus 5x minus 1. So this would be our fraction form. Just so happened we didn't have fraction with that one. And this would be our polynomial form. And again, fraction form is what we normally get up there. So 2x squared minus x plus 4 plus 5 over 2x plus 1. So if we want to write this in polynomial form, we say, well, if we checked it, we'd have to take 2x plus 1 times 2x squared minus x plus 4, but we wouldn't be done, would we? What would we have to tack on? Our remainder of 5. Our remainder of 5, right there in the back. So it's lovely when we get a remainder of 0. You know, that's just perfect world, but it doesn't always happen. So real zeros of our polynomial functions could be rational zeros. Remember, rational means fraction. Use your root word there of ratio. So if we have a rational 0, it's one that could be written as a fraction. And irrational is going to be the nasty square roots that you really can't do anything about. And it's the square roots of primes, actually. Square root of 2, square root of 3, square root of 5. You know, those are, there's nothing we can do with them that's going to give us a perfect answer. You could sure put them in a calculator, but you're going to end up rounding no matter what. So we can get rational, but we can also get our irrationals. So in this one, we see f of x equals 4x squared minus 9, totally factorable. And if it's factorable, we're going to get a couple of rational zeros, -3/2 and 3/2. X squared minus 2, it's factorable, but in a weird way. I mean, we haven't done factoring using roots before, but this would be x plus the square root of 2 and x minus the square root of 2. In fact, most of us would probably solve this one by adding 2 to both sides and then taking the square root. But those are irrational zeros, and it happens. You know, it's the reason we have the whole quadratic formula is for when things don't work out nice. You know, you can make that work. But now we know we could use completing the square for absolutely any of those, and we would be fine. So, this is a good place to stop for today. How are you gonna have to do all 6 of those problems? Long division.
I can't do those. You should like cut it down to like one.
No, honey.